Asking how much traffic can this host handle is a broken question. Provisioning a server based on monthly visitors is a reliable way to overpay for hosting or watch your site shatter under load. Take two identical shared servers. Both receive exactly 50,000 monthly visitors. The first server crashes completely. The second server barely registers any load at all. On the left, a static blog handles 50,000 visitors with a flat load line. On the right, a dynamic membership site serving identical numbers spikes straight into the red. Why? Because an idle browser session is not an active server request. When a visitor spends 20 seconds reading an article, their browser is idle. During that 20-second window, they occupy exactly 0 processing power. True server capacity is determined entirely by the exact number of requests hitting the PHP engine at the exact same millisecond. The primary unit of server capacity on shared hosting is the PHP worker, often called an entry process. This is a rigid, unshareable processing slot. A worker cannot be subdivided. While it generates one uncached page, it remains entirely blind to every other visitor on your site. Once every allocated worker slot is occupied compiling a request, you hit a hard architectural ceiling. No new requests can be processed immediately. Solving this bottleneck requires queuing theory, specifically a mathematical principle proved by John Little in 1961. Little's law relates queue length, arrival rate, and service time. This relationship holds regardless of how many servers exist or the order of service. Provisioning server capacity is an exact mathematical equation. We can calculate your maximum concurrent users by applying Little's law directly to your PHP worker pool. The baseline formula for concurrent capacity begins by dividing your total available PHP workers by your average execution time. This diagram shows an entry-level shared plan. You have exactly 15 processing slots to accept incoming data packets. If generating a page takes exactly 1 second, those 15 slots process a maximum of 15 requests per second. But you can alter the physics of the equation. If you have the execution time to half a second per page, the entire model shifts. The throughput instantly doubles. 30 packets now flow through the exact same 15 slots in the span of 1 second, handling twice as much traffic without changing the underlying architecture. Your baseline capacity is hard-locked by the worker count dictated by your hosting plan. You just cannot conjure a 16th worker. Optimizing database queries to reduce execution time doubles your server's concurrent capacity for free. There is a second, highly volatile variable in the equation, the cache bypass rate. This diagram introduces a massive, semi-permeable filter layer positioned directly above the PHP workers. This caching system acts as a defensive shield for the server's limited processing resources. Watch what happens when 100 requests arrive simultaneously. On a cached blog with a 5% bypass rate, 95 of those packets hit the filter, turn green, and bounce back safely to the user. Only 5 packets pass through to the 15 workers below. In a 100% bypass scenario, the filter opens up completely. All 100 packets smash straight through and instantly bottleneck at the 15 available worker slots. Cached pages are served instantly by the web server's memory. They consume exactly 0 PHP workers. Dynamic, uncacheable requests behave differently. A WooCommerce checkout, a logged-in LMS user, or a personalized membership dashboard bypasses this defensive layer completely. The cache bypass multiplier explains why different workloads demand vastly different resources. Mathematically, a single person checking out of a store requires the same server power as 20 people reading a static blog post. But what physically happens to the 85 excess requests that just slammed into a fully occupied 15-worker server? Exceeding your PHP worker count does not cause the server to crash or immediately reject traffic. This schematic reveals the hidden safety mechanism used by environments like Cloud Linux. There is a timeline-based holding area governed by a 120-second connection timeout. The excess requests are forced into this queue, stacking up sequentially in a holding pattern. They wait for the exact moment a worker slot becomes vacant. The exact amount of time a request spends waiting in this invisible backend line is added directly to the end user's page load time. A stuttering loading spinner on the front end is usually the symptom of a drained queue. Performance degrades gradually as wait time increases. A 503 service unavailable error is not an immediate server crash. It is simply a request that waited in the queue for 121 seconds, timed out, and was finally dropped. We can map this mathematical theory directly onto production limits in the shared hosting environment. This table, the concurrency ladder, maps 3 exact worker allocations against 6 specific WordPress workloads. Isolate the bronze tier's 15 worker column to see how workload type changes everything. At the top rung, those 15 workers easily support over 5,000 simultaneous readers on a cached blog, because the cache hit rate is near perfect. At the bottom rung, those exact same 15 workers will buckle and begin queuing under just 75 simultaneous WooCommerce checkouts. Store owners frequently blame their checkout plugins for failing during sales events. The math proves the plugins aren't broken. A 100% bypass rate is simply overwhelming the available workers. Concurrency capacity is never dictated by your hosting tier in isolation. It is defined by the mathematical intersection of your worker count and your specific workload. When developers encounter a 503 error, their first instinct is often to immediately purchase a virtual private server. This is an expensive mistake. Scaling requires a sequential engineering checklist, starting with the highest yield adjustments. First, aggressively drive your cache bypass rate as close to 0 as possible, using full page caching configurations. Second, for the requests that absolutely must bypass cache, lower their execution time by implementing a persistent object cache like Redis. This side-by-side comparison shows the architectural difference between upgrading a shared plan and migrating to a VPS. On the left is the rigid shared environment. On the right, a flexible VPS mapped to a RAM pool. Upgrading a shared tier from bronze to gold simply buys you a larger block of worker slots, eventually hitting a hard ceiling at 40. The architectural advantage of a VPS is direct access to the PHP configuration. Administrators can dynamically trade raw RAM for custom worker slots on the fly. You only need a VPS when your fully optimized, uncacheable peak traffic mathematically exceeds the 40 worker ceiling of the highest available shared tier. Until you hit that exact threshold, the math says you stay right where you are.